Welcome. In today's lecture, we're going to focus on a concern in machine learning which is very popular nowadays, known as robustness. So up until this point in the course, we've been kind of assuming things are very nice and well-behaved, very ideal, and that, things don't really go wrong. Now, this is nice for when we're just studying things in a self-contained environment, but in the real world, things aren't generally so nice. And we have to deal with cases when things don't quite match our assumptions or the models we use to model the world. For example, you might have heard the phrase that saying all models are wrong, but some are useful. That's kind of the motto behind robustness, because we're going to investigate what happens when our model isn't precisely right in various different ways. Let's talk about why our idealness assumptions might not hold. So, for example, a common thing that we assume is that all our data, when we get it, is generated IID from some distribution which we don't really know, and that's it. This just generated IID, and it's well behaved after that. Sometimes we even assume that we know what distribution it comes from, but in the real world, not all of these might hold. For example, there's several reasons why robustness might be a concern when doing machine learning. One of the classic ones is what's known as model misspecification. So model misspecification is kind of when you assume something about your data, but this isn't precisely quite true. For example, it's a common assumption to make about data to be generated according to a Gaussian distribution, just because Gaussians are kind of ubiquitous. Things often approach Gaussians in many different settings. However, our data is never going to be truly 100% Gaussian. That's really, unless we specifically generate data like that. So it's just an approximation to the truth. So sometimes we actually have to quantify that approximation to the truth. Other common types of ways that robustness might be a concern is maybe we're using equipment which has some sort of error in it. So maybe there's measurement error, which injects maybe some noise into each observation we receive. Sometimes we might have dirty data where there might be errors or things mixed in from other sets. For example, maybe you have one group of people who are collecting information, which is measured in centimeters, and then other people are recording things with inches. Then that would cause issues dirty data. This would cause issues, of course, because you just are kind of measuring things on two different scales. These are all. Let me give you one more example, which is perhaps the type of motivation that most people think about when they think about robustness nowadays, and this is in the presence of an adversary. That is, you imagine that somebody is messing with your data set at some point, or messing with your machine learning model at some point, in order to try to maybe exploit things and make things work more their way. So these are, as I've described, just a number of different ways why things might deviate from our nice idealized assumptions that we often make when doing machine learning. These aren't really technically related. These are just sort of thematically related. We're going to talk, and more broadly speaking, robustness is more a theme rather than referring to a specific problem. Thematically is just asking the question, what happens when things don't go precisely as we expect, and there might be a little bit of variation around what we expect. But we're going to be talking about very specific problems within this framework today. So robustness has been a focus in statistics and machine learning for a very long time, much longer than than machine learning has really even been a field. And I'm going to give you a very simple example that just illustrates, it's a more statistical example, but a simple example which illustrates why robustness can be an issue sometimes and how we can fix it. In some ways, sometimes it's very easy, sometimes it's a lot more challenging. So here's a simple example, one of the most basic situations that we can possibly imagine. So suppose we have x1 through xn, which are generated according to Gaussian with mean 0 and variance 1. So I'm just picking 0 so that we have a fixed mean, but more generally, like you can imagine this is something like, yeah, actually let's just do a general mean, mu invariance 1. So what does this look like? Well, it'll look something like the following. There's some like real line here, and then we have what our Gaussian, something like this, and this is maybe mu. And our data set will look something like this, sparse over here, and more points as we get closer to the mean, and then spread out a lot. So that's our data set, what it looks like. Now, what do we want to do? Our goal is to estimate mu from the data set x1 through xn. So that's our goal. So this is a very simple problem. I think we've probably already talked about it in this class, but if not, it should be familiar to all of you. The easiest way to estimate the mean is just take the empirical mean of our data set. So just average these points. And what we can say is if n is large enough, let's not worry about how large it has to be, what sort of quantitative accuracy we get, but then we'll have that mu hat is approximately equal to mu. So this is a very simple setting where we want to do some sort of mean estimation, and you can see just taking the empirical mean is a very nice, simple statistic that works really, really well. Now, where do things go wrong? Well, like I said, this is a very idealized setting, but things go wrong when we deviate from this, and we will see very quickly that this is not robust. So let's suppose that our adversary, suppose they can add a few points. And just a few, let's say. So, you know, think about an adversary adding, say, 1 or 2 points to this data set. Well, that shouldn't really do too much, right? We have most of the data being nice and coming from this distribution, so we should still be able to estimate the mean, even if we have an adversary who's adding some data points, right? So the first thing I'm going to show you is that, in fact, if we're trying to estimate the mean, and we just try to stick with our current estimator, that is the empirical mean, then an adversary can grossly corrupt the quality of this estimator by just adding even a single point. So I'm going to give you a sec, just think about how they could do that. If you were the adversary and you were trying to mess up this empirical mean just by adding 1 point, what would you do? And just by thinking about it for a sec, you should realize that the right thing to do as the adversary, if you want to cause as much trouble as possible, what you would do is you would put 1 point way, way out, very far to the right, let's say. And yeah, so this is very, very far from the empirical mean, from the actual mean of the distribution. And so if, say, this red point is very large, let's just be concrete. Let's say the red point is greater than 1000 n or 100 n plus mu. Then the mu hat it'll be very far from mu. And again, going with this number, it would be C greater than 100. So yeah, this should hopefully be pretty clear and obvious. What I'm trying to show with this example is if you just consider the empirical mean of a data set, that's often a good estimator for the mean of the underlying distribution. But this is not a robust estimator because of the fact that an adversary can just place a single additional point, which will throw off this the empirical mean by an arbitrarily large amount from the true mean. So this is not a robust estimator. However, there are some things we can do in terms of protecting against this type of adversary. So this is a perspective you should always think about when you're thinking of robustness. there's two parts to any type of robustness setting. One is the attacker, that is how the attacker, how an adversary will maybe add points or change up the setting within the limits of what they're allowed to do. So in this type of setting, the sort of threat model, as it's called sometimes, is that the adversary can add a few points to the data set. So one of the things that they can do, which would grossly corrupt this mean, is by placing a few extra points very, very far. So now, on the other hand, if you're the algorithm designer, if you're the one who's like trying to compute the mean, then maybe you can do something against this. You know that you're going to be attacked, so you should try to protect yourself. Well, in this case, if you know the adversary is doing this, well, there's a very simple strategy that you can do, which is actually pretty good. And all you have to do is take a look at your data set. You'll see that there's one point which is very, very far out and very far off from everything else. So just remove that. So here's one possible defense. Just prune your data set. And this is a kind of underspecified algorithm because I'm just saying prune it. How do you prune it? How do you choose which points to keep and which points to remove? Well, I'm not going to get into that, but this is a valid type of defense if you sort of formalize what this means. And this would actually be a good one. But let me mention another algorithm, which may be a little bit easier and more familiar, which is just take the median instead of mean. And you can notice that if you take the median of your data set, that is the 50th quantile, the 50th percentile of your data set, you'll see that any points that are put very far out, they won't be able to move it at all. It'll be pretty much just shifting the median over by maybe 1 point. So yeah, the median is actually the optimally robust estimator for the one-dimensional setting. So this is like very old statistics, but hopefully this gives you a flavor of the type of stuff that, the type of things you should be thinking about when we're doing robustness. First of all, what is the setting? What is the idealized setting? What would we do in the idealized setting? How are we going to relax that by allowing some sort of robustness? What can the adversary do? What is the best thing the adversary can do? And assuming we have an adversary, what type of things can we do to defend ourselves against it? These are all questions you should be asking, and it's sort of illustrated via this one very simple example before we move on to more complicated things. Yeah, so this is a very simple classic folklore example. There's actually interesting questions, very, very interesting questions about what happens when you consider the exact same problem, except not only in 1D, you look at a multivariate Gaussian, and you want to estimate the mean for that. And a lot of interesting questions pop up, including things like, can we look at points and see if they're individual outliers like this? Like, there's clearly an outlier here, but more generally, will we be able to pick out points like that? Also, we used a median in 1D. Can we do a median in high dimensions? How would we do that? Well, these are very interesting questions, but not stuff we're going to get into today. So feel free to ask me if you're curious and you want to know more about that. But today, what we're going to talk about is what's known as we're going to focus on a specific type of robustness, which is known as robustness to adversarial examples. And robustness to adversarial examples is a very popular area of research right now. In this area of research, there's one very famous picture that everyone shows, and let me just show it to you, and then we'll more formally define what's going on. So here is the perhaps most famous picture that you always see in adversarial examples. So here is a figure which is originally from a paper by Goodfellow et al. And what can we see here? So what is this picture? Well, what we can see here is a bona fide picture of a panda, and all of you would say it looks like a panda. And you can see here what says below it is this is basically indicating that a neural network or machine learning model will take a look at this picture, say, correct, this is a panda, and it's not perfect, but it's pretty good, and it thinks it has a 57.7% confidence that this is indeed a panda. Now, this is nothing special and very kind of normal, kind of what you'd, I'm sure this is nothing surprising at this point in this course. But beyond this is what becomes interesting. It turns out if you take this picture and you add this weird construction here, this sort of random noise looking thing, except scaled down, then you get this picture on the right. And you can see this picture on the right looks almost identical to the original image. You probably can't even tell a difference, right? Well, if you add it on, any of you would still say, okay, this is a panda. But this is where it gets very interesting. The idea here is that instead of saying that this is a panda, a neural network would classify this as a gibbon. And it would actually have a very, very high confidence that this is a gibbon. But of course, it is not a gibbon. So this hopefully shows you what we mean by an adversarial example. We'll be a little bit more precise as we go on, but it kind of shows you the surprising phenomenon that it is possible to find images which a human can easily classify correctly, whereas a neural network will classify it incorrectly. This is kind of the surprising thing, perhaps. You know, we think that like machine learning has solved all the problems in the world and it's very successful at any task we could want to do. But this example shows that in some ways, machine learning is rather brittle, and yeah, we have to really be careful when we're using it and know its weaknesses. So before I continue on, I just want to mention that this looks like, what do? You take something and you add on random noise and then you get something that looks similar. But the thing I want to stress here before we proceed is that this is not random noise. In particular, this is very carefully chosen. This is carefully crafted. And we're actually going to describe how you craft this this sort of image here in order to do attacks like this, so that by the end of this lecture, you'll be able to actually basically figure out this noise as well yourself. So, okay, so this is kind of the idea and the picture you should have when you're thinking about adversarial examples. That it's possible to construct things where there's a discrepancy between what a human would say as well as what a classifier would say. Okay, so let me describe a little bit more precisely. Here's the setting. So suppose we have a model trained on some training data. And this training data is nice and idealized. You know, nothing goes wrong with this training data. It's clean, it's untouched. Life is still normal at this point. So the training, nothing happens in this adversarial example setup. However, what does change is at test time, what the adversary is allowed to do is they are allowed to modify each point a little bit. I haven't been quite precise there, but so yeah, and their goal, the adversary's goal, their goal is to, of course, make the classifier as bad as possible. So reduce the test accuracy as much as possible. So yeah, the thing they want to highlight here is that, again, training process totally unchanged, but the test process is changed in the sense that each image or each feature vector that we're going to try to classify, it'll be shifted or perturbed a bit, and we'll quantify what this means, what we allow to do. Yeah. So let me tell you a little bit more precisely and maybe a little bit more formally what an adversarial example is. So an adversarial example, well, let's say that x prime is an adversarial example for x on model f sub theta if the following two things hold. So one is a kind of informal one, informal for now, informal condition. Informally, we need that x is kind of similar to x prime. Equivalently, another way we can say this is that the distance between x and x prime is small, where we haven't defined what the distance is. And perhaps the least formal but also most evocative way of saying this is that we want really that x and x prime have same label according to a human, let's say, or a perfect classifier. Let's just say a human because we're thinking of pictures for now, but there could be some settings where a human doesn't actually know, maybe some other process. But okay, this first thing essentially says that the two pictures have to look the same in very informal words. So this is an adversarial example for this because it satisfies condition one because this looks like a panda and this looks like a panda. So that's all I'm trying to get across here, that essentially the two things should look similar. The other thing which I can be a bit more precise about for now is the fact that we want that f theta of x does not equal f theta of x prime. So yeah, this essentially says that the label of the original image as predicted by the classifier, this is not equal to what the classifier would predict on x prime. And you can see that in this example here because we have panda here and gibbon here. So it has changed from the original thing. So yeah, that's essentially kind of a little bit more precisely saying what an adversarial example is. They look the same to a they look the same to a human, but they don't look the same to a classifier. So this one, like I said, is well defined, but still number one is not well defined. And why is that? Because we're saying that x and x prime have the same label according to human. It's not clear how to really say that. For example, how do we say that this image and this image look similar without just saying to having a human say that, okay, these two are both definitely pandas? Well, the way to the problem and the kind of open question currently in robustness is how exactly do we encode human perception into a type of distance in order to say that pictures are the same. Unfortunately, it's not clear how to do that. Instead, what we're going to do is we're going to try to encode these images being similar using other ways that are commonly used for saying that points are similar, for example, various distances. So our kind of like what we would kind of like to say is that x and x prime have the same label according to human, that's condition one, but instead what we do is the proxy for human perception in one, what we do instead is we are going to use various distances, use like some sort of distance. This is kind of what I said in the second point here, that we want the distance to be small. So the most common thing is that we use the LP distance. And just so that you recall what the LP distance between two vectors is, it's just going to be, say, x minus, well, what the notation we use is x minus x prime sub p. This is equal to summation of xi minus xi prime to the p whole quantity to the 1 over p power. and where this here is the summation over dimensions of the vector. Okay, so that is the most common type of thing that we use for measuring robustness. And in particular, what we do is that we say that the adversary, they may output any x prime such that we have the following, such as within an LP ball of radius epsilon of x. So let me just say this a little bit more solely. So any sort of x prime which is in something like this. Let me say it like this, in the set of all y such that the LP norm between x minus y is less than or equal to epsilon. So yeah, this is what is known as the LP ball of radius epsilon centered at x. The idea is it's all going to be centered at x, and we're allowed to deviate from that by up to epsilon. Now, and you can think of epsilon, of course, as always being some small number, where small might depend on which p we're looking at. So, okay, I've said LP norms, but there's many different LP norms. There's P for LP for P for anything from 0 to infinity. So which one do people use? Well, people use a number of different ones. For example, they use P equals 0, the L2 norm, the infinity norm, and some others, but these are kind of the most common ones, I'd say. And in today, we're going to focus on L infinity. And the way you can think of L infinity norm is you can change each pixel in an image by up to epsilon in terms of its value. And this is helpful. This is going to be convenient for us mathematically because it'll let us do some nice optimization. There's other things like L0 norm. I'll just point out that the way to think of L0 norm is you can change epsilon points arbitrarily. And L2 norm, well, you should all be familiar with L2 norm, but yeah, L infinity will be the focus on today's class just for simplicity, but you can always switch this for a different type of distance, and most of the things, okay, there's some things like the methods, the attack algorithm that we're going to look at, those are going to be specialized to L infinity, but the same type of setup could also work with any other type of distance we talk about. So yeah, mostly people study LP norms, not necessarily because this really is what an adversarial example is all about. Like, how can you say, it's not clear if you can say that this really encodes that this picture looks like this picture. So it's a bit questionable, but like I said, it's still an open question on how to really encode the idea that these look similar. And in fact, yeah, people just kind of go for LP norms generally because they're mathematically convenient and we can do something for them. There's other types of things that you can do besides LP norms. So let me just briefly mention those. Some things are including Wasserstein distance, which I'm not going to get into too much, but Wasserstein is an important distance in machine learning that you should consider learning about. And another thing, interestingly, is also translations, rotations, and resizing. So for example, what could happen is maybe you have a picture that looks like a 3 or something, and you know, everyone realizes it's 3, and then the neural network says 3. Now, sometimes what you can do is just, even if you don't want to use these adversarial, like these LP norms, one thing you can do sometimes, if you do it right, is you can actually just do a slight rotation. For example, maybe something like this. and this becomes, say, 3. Now, any human would still say, okay, yeah, that's a 3, but it's possible if you do this very carefully chosen type of rotation that a neural network might just totally mess it up. I think it's a 5 or something. So you can, yeah, sometimes rotate it, translate it, move it around, resize it, and if you search correctly and you do it right, then you can turn that into another type of attack. But these are just other things. It's just to say that, like, don't think LP norms are the only things you can possibly do in terms of attacking an image and causing these sort of intriguing properties to fall out. There's other things you can do as well, which are also very damaging. Okay, so hopefully now you get the type of setup in terms of adversarial examples. Let's see how we can make attacks. So we're gonna, like I said, there's always like two parties whenever we're doing adversarial examples or any sort of robustness setting, which is really the attacker as well as the defender. So let's focus on the attacker and pretend we're the attacker for now. So attacker. And what our goal is, if we are the attacker, is the following. So suppose we're given a train model. Just lost this. Let me bring it back up if I can. Cool. Okay, that fortunately worked. Yeah, so suppose we're given a trained model, f sub theta, and we're given a test example, x. Then our goal as the attacker, remember, is to construct x prime satisfying basically the two things that we said before. So the first thing we're going to want is that, first of all, like I said, we're going to focus today on L infinity distance. So we want some x prime such that we have this condition, that x minus x prime is less than, in L infinity distance is less than epsilon. And the second thing we want is that f sub theta of x is not equal to f sub theta of x prime. So hopefully you'll see pretty easily how those match up to the two things we discussed earlier, 1 and 2. And the first one says that x and x prime are essentially the same picture to any human, that it looks similar enough. And this can be done if you take epsilon to be sufficiently small. And furthermore, the second thing says that the classifier does not return the same output when you feed an x versus x prime. Good. So this, hopefully, if you've been following so far, then this shouldn't be anything too surprising. Now let me comment a little bit about this goal for the attacker. Some notes before we proceed. The first thing is that this is a white box setting, or we're going to assume for today's lecture that we are in a white box setting. What does a white box setting mean? It means that we really know everything about this function f, this model f and theta. We know what the parameter vector is, we know what the architecture is, we know how many layers it has, how many neurons there are, and all the parameters, how it was trained. We essentially know whatever we want to know about f and theta. We can, especially important is that we can compute gradients with respect to whatever we want. So that's kind of the first thing that we're going to assume, that this white box. Now, there are some times when we're in black box settings, that in black box settings, maybe you don't know anything about f, you just have that is black box access to it, that in the sense that you can feed in inputs to f and it'll give you predictions. Maybe you just have some approximate knowledge of what the architecture looks like. Maybe you know roughly, you know, it has like 5 layers, but you don't really know what each layer looks like perfectly, etc., etc. So it still is possible to do things in the white box setting when you don't actually have the fully you don't actually have like a full understanding of the architecture and the parameter vector. But at least for today, we're going to focus on the white box setting just because it's conceptually simpler. Cool, so that's one thing. And the other detail, which I haven't really touched on yet, but we'll touch on a little bit more, is the question of what are we trying to do? Let me just write that there's untargeted versus targeted attacks. And by that, I mean that so far all we've been saying is that we want that f of x is not equal to f of x prime. That is, the label of these two things is going to be different. Now, that's nice, and that's what's known as an untargeted attack, just that we want it to be different. But what if in particular, say if we're going back to this example that we've seen before, what if in particular we wanted to misclassify this panda to look like a gibbon in particular? We don't want it to look like anything else, like not like a cat, not like a dog or anything, but we want it specifically to go for this class, which is a gibbon. Well, in that case, that is a targeted adversarial attack. And just to kind of illustrate what this means a little bit more, it would be that f sub theta of x prime is equal to c, which is not equal to f of theta of x for some target c. So this is kind of the replacement of 2 in the case when we're working in a targeted setting, that we want actually that the result is going to be classified as class C, whatever C is, whatever we want it to be, as opposed to whatever it was before, which is not C. So that is, these are both doable in pretty much every setting, both untargeted and targeted attacks. But since it's conceptually simpler, you can probably think of untargeted attacks most of the time. I will comment one thing that we have to change in order to do targeted attacks at one point. But again, conceptually, they're very, very similar. Okay, so now we've talked about what our goal is, what our objective is. Now, it might seem impossible. How are we ever going to do this? This seems totally crazy. But I claim that you already know the answer. You just have to think about the tools that you have. And there's really only one tool that you have when you're doing machine learning optimization, and that tool is gradient descent. So let's be a bit more precise here and see what we're talking about. So how do we optimize a neural network? Or really any sort of non-trivial machine learning model besides, say, linear regression, anything beyond that, you have to use gradient descent. And what do? Like, the way we optimize this is the objective function that we set is we minimize over theta, the following thing here. So this is our loss function. We compute a loss function for each point in our data set, our training data set, and we try to find the theta, which minimizes the sum or the average of these parameter vectors. So let me just note some maybe obvious things here. First of all, the data set is fixed. These xi, yi pairs, these are not things we touch. These are given to us, and we just optimize. We optimize theta while keeping the x and I and yi fixed because they're just data, and we of course don't change it. So yeah, that's the kind of goal here, and the optimization algorithm is just going to be, that we often use, is gradient descent, where theta becomes theta minus eta 1 over n summation of, and here we have gradient with respect to theta of the loss functions. So this is just how we optimize a neural network. Nothing special about robustness. But the thing is that you should get out of this is the fact that really all we did was just set up the loss function. We found which parameter we're trying to change, and that's specifically this parameter vector theta, and then we optimized over it. Well, this is pretty much the exact same thing that we're going to use when we're doing adversarial examples. And the way you can think of the problem is the following. We'll do it generally first and then go into a specific algorithm. Kind of here, we start with the objective function, we went to gradient descent. Well, what we're going to do is we're going to try to maximize this time delta. And let me just write the function first, and then we will sort of discuss it. Okay, so here is what I claim to be the objective function when we're trying to generate an adversarial example for x. So what we're going to do is, sorry, let me just be a bit more precise. Let's say that delta prime is equal to, say, argmax of this, and then we let x prime be equal to x plus delta prime. Okay, so what is this really saying? This is saying that we want to maximize this loss function. We're looking at the loss function at one particular point, which is x, y, and theta. And we're really trying to modify this x such that it maximizes the loss. So remember, before what we were trying to do is minimize the loss so that it is kind of going to guess the right label as much as possible. But here, when we try to maximize the loss, that's trying to do the opposite. It's trying to say that we are trying to make sure that the chance that it predicts the right label is as low as possible. Therefore, we're going to be modifying the x. And how do we modify this x? Well, you'll see that we're basically just adding on some delta. This delta will be a vector of the same dimensionality. Let me maybe be clear about that. Delta isn't going to be an r to the d. And in particular, we also have this constraint saying that the L infinity norm of delta is less than or equal to epsilon. And why is this? Well, remember, our goal is to have that x minus x prime in L infinity norm is less than or equal to epsilon. Therefore, we're going to try to have that delta has L infinity norm less than or equal to epsilon. Because, yeah, this will result in x prime having the desired condition. So, yeah, this is interesting because note how similar it is to our previous optimization function, except now we have the fact that theta is fixed, but now we're trying to optimize over the specific data point. We're trying to find some perturbation of this data point, which gives us this a loss which is as large as possible. And okay, so here is the optimization problem. The question is, how do we optimize this? Well, there's exactly one algorithm that we use for optimizing these types of things. Well, okay, not strictly true, but like the most common one is just use gradient-based optimization. And the main way you might think of solving this first is just use gradient descent, and because that serves very well. But the thing is that this time we have this constraint here that we have that the L infinity norm of delta has to be less than or equal to epsilon. So this causes a bit more of a challenge. It's not going to be quite as trivial or quite that easy. So, but instead what we're going to do is, I'll show you two different algorithms. One is going to be very, very fast, very efficient. And then I'll show you another one, which is slightly slower, but actually more powerful in the sense that it can give you better attacks. So this is the first one, and simple, and it's called the fast gradient. I don't know if there's actually a hyphen here, but it's the fast gradient sine method, or the FGSM for short. And let's derive this real quick. It's very simple, actually. When we're doing any sort of gradient-based optimization, what do we always do? Well, what we do is we just compute the gradient with respect to the parameter that we're looking for, that we're looking to optimize, rather. What we do is we compute gradient with respect to delta of L x plus delta, or comma y, comma theta, where delta is our current, well, okay, actually, let me say it like this, because we start with it equal to 0. We just compute the loss like this. No, let me leave this in, actually. Y theta. And the idea here is that we're going to start with the 0 vector for the delta, because it's just going to be initialized to 0. But we're going to essentially see what we can do, what direction is the best and if we want to really optimize this function and we want to maximize it. So this kind of tells us a direction to take a step in. So if we were just doing gradient descent, we would just repeatedly take steps in this direction, and then when we're done, we're good and we have an optimized function, hopefully. Now, this would be nice, but it isn't that easy, because we, in addition to just trying to maximize this function, we additionally have this constraint. So what we're going to do is we're going to take a step in this direction, of the direction of this gradient, but subject to constraint. So what we're going to do is take a step in the gradient direction, subject to constraint. And let's be a bit more precise, like kind of try to take the biggest step you can in that direction, subject to this constraint. So let me draw you a picture of what I mean by this. So let me draw it right here. We have a bit of space here. So what I'm going to draw here is, this is a kind of two-dimensional picture of what delta looks like. So this is minus epsilon, epsilon, this is minus epsilon, epsilon. So the 2D caricature of what delta might look like. And initially what we start with is delta equals 0. And what the idea is, recall that we want to find some delta which optimizes this function, subject to the fact that the L infinity norm of delta is less than or equal to epsilon. Well, the way that what that means is, if you like sort of think about it a bit, is that the vector in terms of what delta is going to be lies somewhere in this box, kind of axis-aligned box, and 2D is just a square. But we really need that the delta is going to be within this box. So the way we can find the way the FGSM works is, what we're going to do is we're going to try to just see what the gradient takes us and push that as extreme as we can go. So let me draw a picture of where, like, let's suppose our gradient looks something like this. Something like this, maybe. Points in this direction. And this delta. Now what the FGSM does is it kind of takes this, the way this is pointing, and it pushes it as extreme as we possibly can. So what we're going to do is we're going to take it, see, okay, it's pointing, should we go up versus down? It says, okay, maybe up is a better direction. So we're going to push that as far as we can. And is it saying to go left or to go right? Well, it says to go left because this is pushing more in that direction. So we go here. And overall, our the point that we're going to return is delta is equal to this value. So this right here is going to be delta. So that's the main idea. We just look at the gradient and we kind of push it to the corner of this box. Let's be a little bit more mathematical about what we mean by that. Well, the way we translate this red step into math would be that delta star, let's call it delta star. This is going to be equal to epsilon times the sine of gradient with respect to delta of loss of x plus delta y theta, where delta initially starts in the whole process as 0. So this is all we have to do. And let's try to see how this maps up to what we were doing before. Well, like I said, this is just the gradient. This is going to give us a vector. And we take the sine of it. And that just basically means that, for example, let's take a look at the x-axis, the x-coordinate. We're trying to, what we do is we see whether it's pointing left versus right. And we can see that the gradient is pointing left out of these two directions. So therefore, taking the sine will give us a -1. And then we put a -1 times epsilon, which pushes it all the way over to this side, as opposed to this side. And similar logic goes for the other coordinate. In terms of picking whether we want to go up or down, well, we see that the gradient is pointing upwards. So we therefore push it to the top edge of the box, this edge instead of this edge. And putting those together in both coordinates, we get something over here. Yeah, so hopefully that's clear. We just kind of take a look at the gradient and push that to the corner that's kind of roughly pointing towards. And in particular, this will always give us a point, a delta star, which is then plus minus epsilon to the d, where d is again the dimensionality of the input. So hopefully this is clear. This is the fast gradient sine method. This is a pretty good method for a few reasons. One is that it's reasonably good in terms of attacking. It's powerful. It can reduce the test accuracy quite significantly. And also on top of that, it's very, very fast, because all you have to do to attack each individual point is you just compute the gradient. And you don't even have to compute the gradient very exactly. You just have to get some signs, which can be even faster sometimes. And then based on the sign vector, by sign I mean each entry of this vector will be plus or minus 1, then you just rescale that by epsilon, and that'll take you to a corner of the box. So this is very, very fast to implement. The downside of the fact that there actually exists stronger attacks. So let me hopefully this intuitively makes sense. Let's talk about something a bit more powerful, which is known as projected gradient descent. Or PGD for short. This is basically the multi-step version of this. Like, you might be thinking, your criticism of this approach might have been, oh, it was just saying to go here. Maybe this is the right place to go. There's no need to push it all the way to the corner of this box in order to get the right answer. And what PGD does is essentially prevents you from slamming all the way into a corner of this box if that's not the best thing to do. So what you do is the following set of iterations. I'll write it out first and then we'll discuss it. So this is the projected gradient descent approach, and you just repeat this several times. Let's talk about what this means. So what we have in the middle here, well, this is exactly just standard gradient descent, or I guess gradient ascent in this case. So you'll recall that this is a maximization problem. So with maximization problems, we actually do gradient ascent instead of gradient descent, but that's no big deal. You'll recognize this as very, very similar to what we had before. The only difference is the fact that instead of doing epsilon, which will push it to the corner of the box, well, instead what it'll do is it'll just put an eta here in order to, where eta is some sort of hyperparameter. So same as before. But eta, terrible eta. Eta is a hyperparameter. Okay. Now the other thing to note is the sort of where does this projected part come in? Well, it's this part here, this projection step, which takes us back in the set. I think I've already described this before, but let me just make sure we're clear here. So let me draw the same picture that we had before, which was something like this, minus epsilon, 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 epsilon. And so the idea is the following. Imagine we were just doing steps like this, then this would be something like the following. Well, we start at 0, and then maybe we take some step like this, we take some step like this, take some step like this, maybe take some step like this, and so on. But the thing is, eventually, if you take enough steps like this, it's possible that you might get outside of this box and you can just keep going, and eventually just like leave the box entirely. So that's no good, because why is this not good? It's because of the fact that when we were trying to optimize delta, what we really wanted was a delta, recall, with this condition that delta in L infinity norm is less than or equal to epsilon. And if we just keep optimizing it and take us further and further away from this L infinity box then we are not really satisfying, and it'll essentially it won't really be an adversarial example because it'll take us to some picture that maybe looks nothing like the actual target. Good, so this is kind of a problem. So instead what this projection step does is essentially after each type of step it does, if we go outside of the box, then let's take it back in. So in fact, what would happen is something more like the following. We would take steps like this as normal, but then maybe we take this step, and then after this step is done, then what we do is we clip it back into this box right here. And then maybe the next step tries to go this way, and then this takes us back into the box, something like this, until eventually we get here, maybe, and this is where we decide to stop. So the idea is that proj, so this just projects into minus epsilon epsilon to the d if necessary. Yeah, and this will, as a result, make it so that each of our iterates, each delta t, is going to actually be within this L infinity ball. And this is actually a very easy projection step to do. Sometimes projections can be very complicated functions and stuff like that. But here, projecting into this L infinity ball is very easy to do, just because all the L infinity ball says is it says that each coordinate is going to be less than or equal to epsilon in terms of absolute value. So what you can do is just see if any of your coordinates are greater than or less than epsilon or minus epsilon respectively. And if they're outside these bounds, then you just clip it to the relevant coordinate. So let me just give you an example. Say we have project of like, I don't know, 3 epsilon and then minus 2 epsilon. And we have 0.5 epsilon, something like this. This will be equal to, so this is larger than epsilon, so it just becomes epsilon. And this is less than epsilon, so it becomes minus epsilon. And then this one here, it's within the bounds, so it just stays what it is. So hopefully that's clear what we mean by projection. Okay, the last thing I want to mention, oh yeah, this is why this is good. This is good because it's more powerful than FGSM. It can lead to better attacks, which reduce the accuracy much more, and yeah, the downside is that it's slower to run because, for example, you need to run many steps of gradient descent for each example, and also there are hyperparameters such as eta, which are a problem. Makes it a bit trickier, but nonetheless, it can be worth it because it'll lead to often better attacks. Yeah. In particular, just to say what I mean by that, maybe this has gotten a little bit abstract, but for example, this type of picture we have here, maybe if you optimize it via FGSM instead of PGD, I'm not sure which this one in particular was done by, but if you optimize via worse optimizer, you might need to increase the value of epsilon in order to get a good adversarial example. And if you increase the value of epsilon, then that'll look less like the original picture. So yeah. Basically just that better optimizers will optimize better, perhaps tautologically. But yeah, and the sort of end goal down the pipeline will be the fact that there'll be a smaller distance between your original image as well as your adversarial example image. Okay, the final thing I'll talk about before we move on to talking a little bit about defenses is the fact about the loss function. So remember, at this point, we've been talking about untargeted. And for untargeted, remember where we just want to basically make the classifier make a mistake on this input. What we were looking at was maximize over delta, x plus delta, y, theta, such that to norm of delta and infinity is less than or equal to epsilon. But what do we do differently for when we're doing targeted attacks? And in particular, we're going to imagine that we want to change the label from whatever it is, from y to some other target c. Well, what we're going to do is we are going to also set up a maximization problem, but what we're going to do is we're going to do two things. One, we want to make it maximize its loss in terms of getting the original thing. So let me write this first. What this term here says is the exact same as before, but what this says is try to make sure it pays as much as possible if it predicts the correct label. And the other thing that we want to do is the following term right here. And we're trying to say here, pay as little as possible for predicting that the label is C. So you can see that you're both trying to penalize it for getting what is actually the true label, but reward it for predicting the label that we're trying to target. And then as before, we just still have such that the L infinity norm of delta is less than or equal to epsilon. Cool. So that's the main difference between targeted and untargeted attacks. But you can see how minor a difference it is. It's really just the same thing. You just swap the loss function a very little bit, and then essentially everything runs fine just as before. So, okay, that's basically how we generate adversarial examples. It's I think, a really interesting and cool type of thing you can do. It's surprising that this is so effective in the sense that I'll show you a bit more in some examples, but essentially, if you just train a neural network model naively, then it's possible to attack pretty much every single point in its test set. So even with a fairly small value of epsilon. So essentially, you can make adversarial perturbations to pretty much every point in the test set. And even though a human would get them all right, a neural network classifier would get them all wrong. That's the kind of surprising thing, the fact that these attacks are really universal and can affect pretty much every point. So let's talk about what do you do against this? This is really crazy. Can we protect ourselves against it? So up until this point, we've been really wearing our attacker cap, but now we have to think about things from a defender perspective. So now when I say about our goal, I'm going to be talking about our goal as the defender. And what is the defender trying to do? The defender is trying to make sure that even if there's an attacker who's trying to do sneaky things like this, like maybe FGSM or PGD attacks, or really any other type of attack, basically, as long as the adversary is trying to do, the attacker is doing something like this, then we're trying to make sure as the defender that our test loss does not go down that much. And there's a pretty natural, there's many different defenses which have been proposed. One good one, relatively good one, is known as adversarial training, is what I will describe to you. And so let's talk about what adversarial training is, and I'll try to motivate it for you. Let's first talk about what our loss function is generally when we are doing training of a neural network usually. Our usual goal is the following, that we want to minimize over theta the expectation of x, y, p of L, x, y, theta. So this is our usual goal when we're doing sort of some optimization problem. We're trying to choose the theta such that if we got a new sample from whatever distribution our data comes from, then the loss is going to be kind of minimized. Now, in the robust setting, it changes a little bit. I'm going to write it out first, then we can discuss it. Yeah, this is what the loss function that we're going to try to consider in the robust setting is. And this is pretty intuitive to understand why this is the right thing. So before we were just saying that, okay, suppose we draw some example from the test data set, and then we try to compute the loss function. We really want that expected loss to be small. But now, remember in the robust setting, we're imagining that the adversary can modify each point in the test set. So now what we do is we imagine the following. we imagine that we draw a point x comma y from the data set, and then this is fed into the loss function. But before the loss function is really computed, the adversary, we look at the max possible value of this loss function over all possible delta, which are valid perturbations of the point x. So yeah, now you can see that this is going to be strictly greater than it was before, because really we also have this additional step of this adversary who's trying to attack the point. And then we minimize the theta over all of this. You can see this becomes more complicated because instead we're optimizing this function with respect to theta, and inside this expectation we have this max. So it's not really clear. This is kind of our objective that we try to optimize, but it's not really clear how to optimize it directly. And the way we'll do it is kind of as follows. We're going to look at the following. So our objective function, in terms of like, this is the goal, but our concrete objective that we're going to try to optimize on our data set is going to be something more like this. So you can see here, this is pretty much the same thing, except I just replaced this expectation with an average over our test data set, or sorry, our training data set. Yeah, besides that, it's the same thing. You'll note that each point here in the training set may have its own perturbation. And so the way to interpret what this is really saying is when we're training, instead of just training on the points themselves, the xi's, what we're instead going to do is we're going to perturb each point in our training set as much as we can to sort of increase the loss, and then train on that. So this is kind of interesting. I think this is a neat conceptual point. So we were talking before about how to be a good attacker, and what we were doing was we were really maximizing this function here when we were an attacker. And now what I'm telling you is that if you want to be a good defender, then you're actually going to have to be a good attacker as well. So let's write out the steps of how to solve this in practice. So solving this itself is actually not easy if you want to solve this like exactly what it says here, but instead we're going to use approximations which turn out to be good enough in practice. Like if you really want to optimize this, you kind of have to optimize these both simultaneously, but in practice what we're going to do is we're going to solve this inner problem and then we're going to solve the outer problem. So what we're doing when we're training is we're going to draw mini batch B, just to sort of say we have a small set of examples. And then what we're going to do is for each point in this mini batch, what we do is we compute the best possible attack for it. And this is just going to be like this. So yeah, this is essentially the exact same loss function that we've seen before when we were trying to optimize as the attacker. You'll recognize it as pretty much exactly this. So that's the exact same thing we're doing here. Let me also comment the fact that theta is the current set of parameter vector of the neural network when we're training. Let me try it. Yeah, this is going to be the current parameter vector when we're training. And again, we can have a different type of perturbation to each individual point. So, okay, essentially we like use methods above. Well, let me say. And the last step in our training procedure before we repeat is we just update our gradient. We say gradient, or sorry, update our parameter vector. Just like this. Okay, good. So, and then 4 is repeat. And you repeat this many, many times until overall you're done, until you're sufficiently optimized. Okay, so this is a very simple idea where you draw a mini batch from your training data set, and then for each point in your mini batch, what you do is you try to attack it as well as you can using the current set of parameters, and then you take a step based on the loss function at these attacked points in your training set. And yeah, I think this is conceptually nice because, like I said, you have to harness the power of an attacker in order to be a defender, in order to do this adversarial training. And it turns out that this works pretty well in practice. And in fact, the quality of your defense, let me be clear what I mean by a defense, because imagine you train a neural network and you don't train it, you just train it naively. Well, using the methods we've already discussed, you can take the accuracy effectively down to 0. It'll get every single point in the test data set wrong. But instead of doing that, if you instead train it using this type of approach, where you do this adversarial training, then after you do this adversarial training, it'll perform much, much better in terms of the robust accuracy. That is, the adversary can still try to attack every point in the test set, but it'll be much less successful if you train it like this, because you've kind of, in some sense, prepared the network to handle this type of attack. So yeah, this is perhaps one of the better types of defenses that we know, adversarial training. I will warn that defenses seem to be much harder to pull off than good attacks. For example, I told you this attack, these attacks which I described here, FGSM, PGD, if you understand these well, then you can attack a lot of different networks, whereas defending is a much more tougher thing to do. Let me give you one sort of cautionary tale, and this is essentially a paper due to Atelier, Carlini, and Wagner from, I guess it was 2018. And so there's a nice little story. So what happened was there's a few different big conferences in machine learning. One of the big ones is known as ICLR, ICLR. So ICLR, it has this very unique, relatively unique feature where all the papers that are submitted to ICLR are publicly visible. Anyone can see what's been submitted and read all the results and see what the latest work is, which is kind of unique. Otherwise, papers are hidden during review time. So this is very interesting because what the authors of this paper did was they looked at all the different results which were submitted to ICLR and found the ones which were on adversarial defenses. So there's many, many different papers, and they still are many papers which try to claim that, oh, adversarial examples are a problem. Well, we have this new technique which will fix all your problems. And they'll defend against adversarial attacks. But of course, it's very, very difficult to be able to be confident that your defense is really, really good, because it's always possible that someone might come along with a better attack and break your defense. So this is the tricky part about building a good defense, in the sense that for a defense to be good, it really has to work up against every possible attack, even ones which haven't been discovered yet. So the thing is, back at this point in 2018, people were a little bit naive and just thought, okay, let's do some sort of heuristic defense. Maybe it'll do well. But these three researchers were having none of that. And so what they did was, okay, eventually ICLR does reviewing and they released their decisions. And in the accepted papers, let's say ICLR 18, they accepted 9 papers on defenses. Let's say adversarial defenses. So these were systems or algorithms which for training, which said if you train via our method, then in fact you'll be impervious to adversarial attacks. Well, what they were doing during the time while the review process was going on was they were showing that this is actually nonsense, and they managed to break 7 out of those 9 papers which were just accepted basically the day after decisions were posted. So let me show you this chart and interpret it. So here are the 9 papers that were accepted to ICLR, which were on adversarial defenses. And you can see that they had okay, they claimed some sort of better accuracy under adversarial attacks, but this paper produced new attacks which reduced the accuracy of all these different methods from whatever they claimed 90 something down to 0. So essentially every single point nonetheless can be attacked using this Atelier et al. Method. Yeah, 6 of them can be attacked very, very thoroughly. This one, I can't remember why. It doesn't work. And then these 2 are the ones which seem to use different methods, which don't rely on a method known as obfuscate gradients. But importantly, this paper, Madri et al., is one of the ones which really developed the method of adversarial training that we talked about over here. So you can see that while pretty much everything else goes to 0, this one remains at 47, which is actually pretty good for such a hard task. So yeah, it might seem bad accuracy, 47%, but robustness is a very hard problem. So yeah, this little story I think is kind of interesting, and it's just a real warning to say that yeah, defenses are very hard, and in fact harder than attacks. Like the one way which is not quite precise that you can say it is that really attackers are winning in this battle of adversarial examples, because it seems like they can destroy more settings, pretty much every setting, while defenders can't really do that well, since 47% accuracy is not that great nonetheless. So yeah, just be careful. I want to talk briefly, we'll just wrap this up. I just want to mention that there's like, I think it's just compelling enough, maybe just seeing this type of example here with like the panda to gibbon and how well it is, but it's not quite that limited in the sense there's other things that these can do as well. And let me share with you one video which I think is very exciting. The fact that this totally blew my mind the first time I saw this. So this is a what is it? This is an adversarial 3D printed turtle. So this, yeah, let me show you here. So this is a, it says, let's have this sped up. Let me do it normal speed. So you can see here, this is a regular turtle, like a toy turtle rather. And you can see that if you show it, then if you say pause at any time, like no matter which angle you hold it at, this classifier, this Google Inception v3 classifier, which is kind of state of the art at the time, it's going to say that it is some sort of turtle. So terrapin, leatherback, loggerhead, apparently these are all types of turtles. So yeah, it pretty reliably from all angles says that this is indeed a turtle. But now the really cool thing is that these researchers, they made an adversarial turtle, which is actually classified as a rifle. So you can see that this 3D printed object that they made, if you hold it up, this classifier will nonetheless think that it's a rifle, even from all sorts of angles. And it's due to this kind of funny texture that it's got here, which isn't quite perfect turtle-like, but it manages to fool the classifier. And for example, this baseball here, which looks kind of like a baseball, 3D printed baseball, well, it's classified as an espresso. Maybe you can see the textures a bit. But nonetheless, I thought this was really cool, and it's work by these 4 guys. These 4 guys, Atelier, Angstrom, Ilias, and Kwok. So yeah, this shows that how powerful these attacks can be. They really show that even these 3D printed things, you can hold up whatever angle, and they still look like they can fool image classifiers. So that's one, I think, kind of cool thing that's beyond this. The last thing I'll mention also is, just very briefly, I want to mention backdoor attacks. Now, the idea behind backdoor attacks is actually a slightly different setting than what we've talked about so far. So far what we've talked about is when the attacker can only modify the test set. And by modifying the test set, then they can do some pretty cool and evil things. Now, the question is, what a backdoor attack is when they can do more than just affect the test set. It's when they can also affect the training set. So the idea is that if an attacker can affect both the training and the test set, then somehow that gives them more power. So let's say that the model here is, I'm not going to be too precise here, but the model is going to be that, first of all, they can attack points in the test set, kind of as we discussed, but they can also modify some points in the training set in a similar way. So let me give you an example of what I mean. So here is an example of a, this is a stop sign, and you can imagine that maybe in the training data set, you can perturb these points in a very similar way. So a small number of pixels maybe can be changed. So most of the picture is not changed, but right here in this place, we're just going to put a yellow square, and then that's sort of like these different little changes to it can all be seen as types of perturbations of the original image. And then we can train it appropriately on these like perturbations of the original image. This is kind of our backdoor that we're setting up. And I'm not going to go too much into details, but the idea is if you do something like this, then there's some really cool things can happen. So if you do something like this, then this is a real stop sign in the physical world. This is somewhere near NYU in New York City. You can see that the researchers, this is a result by Gu, Dolan, Gavitt, and Garg, but you can see that they put this sticker on the stop sign in the real world, and this caused that their image classifier, which has been trained in the sort of subject to a backdoor attack, it actually classifies the stop sign as a speed limit sign instead with very high accuracy. So this maybe gives you one indication of why this type of robustness should be something that you're worried about, because in fact it can, you can imagine that this type of thing could throw off self-driving cars quite significantly if something like this were done. Cool. So yeah, overall, this is today's lecture on adversarial robustness. It really serves to show how vulnerable machine learning models are to small changes. And while they seem unlimited in terms of their power, they're really sometimes quite brittle. And that's something you should be aware of and careful of in terms of any sort of deployment.